Picture this. You're standing in the scorching Persian desert in 900 CE, watching what looks like pure magic. Water is flowing steadily through channels, filling gardens and turning mill wheels. But there's no river in sight, no pumps, no visible source. Just crystal clear water appearing from underground tunnels that stretch for miles beneath your feet. The locals call it a Qanat, and what you're witnessing is one of humanity's most ingenious engineering feats. But here's the thing that'll blow your mind. This isn't some ancient mystery we're still trying to figure out. We know exactly how they did it, and the methods these Persian engineers used were so brilliant that some of their Qanats are still delivering water today, over 1,000 years later. We're talking about a technology that makes our modern water systems look like toys in comparison. You might think these ancient builders had some kind of supernatural powers or lost technology, but the truth is even more impressive. They accomplished this miracle using nothing but hand tools, gravity, and engineering knowledge that would make modern surveyors jealous. No machines, no electricity, just pure human ingenuity and backbreaking determination. The numbers alone tell an incredible story. A single Qanat system could stretch for dozens of miles underground, requiring hundreds of precisely placed vertical shafts and tunnels carved through solid rock. The margin for error was practically zero. Get the slope wrong by even a fraction and months of work would be worthless. Too steep and erosion would destroy the channel. Too flat and the water would never flow. These engineers had to be perfect every single time. What makes this even more remarkable is that they were working completely blind for most of the construction. Imagine digging a tunnel the width of a small closet, following a grade so precise that it drops just 1 foot for every 1,000 feet of distance, all while working by candlelight dozens of feet underground. One wrong calculation, and you might miss your target by hundreds of yards. Before we dive deeper into this incredible story, make sure to hit that subscribe button and give this video a like, and definitely drop a comment about what you find most fascinating about these ancient water systems. Trust me, by the end of this series, you'll have plenty to say about the genius of Qanat construction. The story begins with something most people would never notice. A surveyor standing on a hillside, squinting at the horizon with nothing but his eyes and some basic tools. But this wasn't casual sightseeing. This man was about to perform calculations that would determine whether an entire community would have water for generations to come. These surveyors were the unsung heroes of Qanat construction. They had to identify the perfect source in the foothills where underground water was abundant enough to support a major project. But finding water wasn't the hard part. The real challenge was calculating a route that would carry that water dozens of miles to where people needed it, maintaining just the right slope the entire way. Here's where it gets fascinating. The surveyor would use a technique called water leveling that was so accurate it puts modern laser levels to shame. They'd fill a long tube with water, holding one end at the source and stretching it toward the destination. Since water always seeks the same level, they could measure elevation changes across vast distances with incredible precision. It was like having a flexible ruler that could bend around mountains and valleys. But the real genius was in reading the landscape itself. A skilled surveyor could look at a hillside and see things invisible to everyone else. The way certain plants grew indicated underground moisture. Subtle changes in soil color revealed different rock layers. Even the morning mist patterns could tell him where water was hiding beneath the surface. Once the route was planned, the first major construction step was sinking the mother well. This wasn't just any hole in the ground. This deep shaft had to penetrate through layers of soil and rock until it reached the aquifer, the underground water source that would feed the entire system. Some of these wells went down over 300 feet, all dug by hand with primitive tools. The men who dug these wells were a special breed. They worked in shifts, lowering themselves into an increasingly deep hole on crude rope ladders, chipping away at rock and hauling up buckets of debris. The deeper they went, the more dangerous it became. Cave-ins could bury workers alive, poisonous gases could accumulate at the bottom, And all the while, they had to maintain perfectly straight walls and exact dimensions. But the mother well served a crucial purpose beyond just reaching water. It was their proof of concept, their way of testing whether the underground source was strong enough to justify the massive project ahead. Workers would monitor the water level for weeks, checking how quickly it recharged after being emptied. If the flow wasn't sufficient, the entire project would be abandoned before it really began. Assuming the mother well passed the test, the real work could begin. And by real work, I mean one of the most ambitious construction projects in human history, carried out entirely underground by teams of workers who had to be part miner, part engineer, and part magician. The basic concept sounds simple enough. Dig a series of vertical shafts down the slope from the mother well toward the destination. Then connect these shafts with a horizontal tunnel that maintains the precise grade needed for water flow. But the execution was anything but simple. First, they had to calculate the exact spacing between shafts. Too far apart, and the horizontal tunneling would become impossible. Too close together, and they'd waste enormous amounts of time and labour digging unnecessary holes. The typical spacing was around 30 to 40 metres, but this varied depending on the terrain and soil conditions. Each shaft had to be positioned with surveying accuracy that would impress modern engineers. Remember, these workers didn't have GPS or laser theodolites. They used stretched cords, plumb bobs, and their own eyes to ensure that every shaft was perfectly aligned with the overall route. One misplaced shaft could throw off the entire tunnel system. The shaft digging itself was a study in organized chaos. Workers would form human chains, passing buckets of dirt and rock up from the bottom, while others descended with fresh tools and supplies. The sides had to be perfectly vertical and properly reinforced to prevent collapse. In unstable ground, they'd line the shafts with stone or brick, creating permanent structures that could last for centuries. But here's what really showcases their engineering brilliance. These shafts weren't just access points for construction. They were integral parts of the finished system, providing ventilation and maintenance access for the completed Qanat. The spacing and design had to account for airflow patterns, ensuring that workers could always breathe safely while maintaining the tunnel system. The horizontal tunnel connecting these shafts was where the real magic happened. Working in spaces barely wide enough for a person to crawl through, teams of diggers had to maintain that critical grade of about 1 foot of drop per 1,000 feet of distance. Too steep, and rushing water would erode the channel. Too flat, and the water would stagnate or stop flowing entirely. The tools were primitive by our standards but perfect for the job. Short-handled picks for breaking rock, small shovels for moving debris, oil lamps for light, and most importantly, measuring devices that could check the tunnel grade with incredible accuracy. Master diggers used weighted strings and notched measuring sticks to ensure every foot of tunnel maintained the proper slope. The spoil removal was its own engineering challenge. Every bucket of dirt and rock had to be hauled up through the vertical shafts by hand. On a major Qanat project, workers might remove thousands of tons of material, all carried to the surface one leather bucket at a time. The logistics alone would challenge a modern construction company. What's truly remarkable is how these ancient engineers solved problems that still challenge us today. They figured out drainage, ventilation, structural support, and precision grading using nothing but observation, experience, and mathematical principles that wouldn't be formally codified for centuries. This was just the beginning of the Qanat construction process, but already you can see the incredible level of skill and planning required. These weren't primitive people stumbling around in the dark. They were sophisticated engineers executing complex projects that required knowledge of hydrology, geology, surveying, and construction management. But the horizontal tunneling was where things got really dangerous. We're talking about working in spaces so cramped that a modern safety inspector would have a heart attack just looking at them. These tunnels were typically only about 3 feet high and 2 feet wide, just enough room for a person to crawl through while swinging a pick. And remember, this was all happening dozens of feet underground in complete darkness, except for flickering oil lamps. The master diggers were the rock stars of Qanat construction. These guys could feel their way through different types of soil and rock, knowing instinctively when they were hitting hard clay that would hold its shape versus loose sand that needed immediate reinforcement. They developed an almost supernatural ability to maintain the proper grade while working hunched over in pitch-black tunnels. One veteran digger supposedly could tell if the slope was off by even half an inch just by the way water pooled in the bottom of the channel. Here's something that would make any modern worker quit on the spot: the air quality. As the tunnel got longer, fresh air became scarce. Workers would literally gasp for breath while trying to swing heavy tools in cramped spaces. That's why the shaft spacing was so critical. It wasn't just about construction access, it was about staying alive. The alternating open shafts created a natural ventilation system that pulled fresh air down one shaft and pushed stale air up the next. The really clever part was how they dealt with different ground conditions. In loose, sandy soil, they dig slightly larger tunnels and line them with stone or brick. In solid rock, they could get away with smaller spaces but had to work much slower. Some sections required timber supports, which meant hauling wooden beams down through those narrow shafts. Try fitting a 10-foot beam through a hole barely wide enough for your shoulders. When they hit water-bearing layers, which was the whole point, things got both easier and more complicated. Easier because they knew they were on the right track. More complicated because now they had to work in mud and standing water while trying to maintain precise measurements. The experienced crews actually celebrated hitting these seeps, even though it made their job harder. It meant the Qanat would flow when completed. The coordination required was mind-boggling. Multiple crews worked simultaneously on different sections of the tunnel, all proceeding toward predetermined meeting points. Imagine trying to dig from both directions and meeting perfectly in the middle, underground, with nothing but rope measurements and basic geometry to guide you. Get it wrong, and you'd waste months of work digging tunnels that never connected. But they didn't just dig straight lines. Smart Qanat builders incorporated subtle curves to follow the natural contours of the underground geology. They'd bend the tunnel slightly to avoid hard rock formations, or to follow water-bearing layers. This required even more sophisticated surveying, since they had to calculate grades along curved paths while working entirely underground. The debris removal got more challenging as the tunnels got longer. Picture this. You're the guy at the far end of a tunnel that's now half a mile long. Every bucket of dirt you dig has to be passed hand to hand through that entire distance, then hauled up a vertical shaft. By the time spoil reached the surface from the deepest parts of the tunnel, it had been handled by dozens of different workers. The logistics were like an underground assembly line running in reverse. Some of the larger Qanat projects employed hundreds of workers organized into specialized teams. The master surveyor planned the route and monitored progress. Master diggers led the tunneling crews and made critical decisions about construction methods. Haulers moved materials up and down the shafts. Support crews maintained tools, provided food, and handled the million little tasks that kept the project moving. The most dangerous job belonged to the workers who had to venture into unstable sections to install reinforcements. When a tunnel showed signs of potential collapse, somebody had to crawl in there with stone blocks or timber supports and shore it up before the whole section caved in. These guys were basically underground first responders, except their emergency room was a cramped tunnel that could bury them alive at any moment. Quality control was literally a matter of life and death. The foreman would regularly check the grade using weighted cords and measuring devices, ensuring that every section maintained the proper slope. Too steep in one section could create erosion that would destroy the entire channel downstream. Too flat, and water would back up, potentially flooding the work areas and drowning the crew. But here's what really shows their engineering sophistication. They built in features to handle problems before they happened. At natural breaks in the slope, They'd construct small settling basins where silt could accumulate without blocking the main channel. They created overflow channels to handle seasonal flooding. They even built inspection chambers at regular intervals where maintenance crews could access the tunnel for cleaning and repairs. The tunnel floor itself was a work of art. In sections with good bedrock, they'd smooth it to a perfect grade, sometimes even cutting shallow channels to guide the water flow. In areas with loose soil, they'd line the floor with flat stones, creating a durable surface that could handle centuries of water flow. Some Qanats had floors so perfectly constructed that they're still smooth after 1,000 years of use. Temperature control was another brilliant innovation. Deep underground, the water stayed naturally cool, a huge advantage in the desert heat. But maintaining consistent temperatures required careful attention to tunnel depth and insulation. Workers would sometimes pack clay around sections of the tunnel to prevent heat transfer from surface layers. The really advanced Qanat systems included branch tunnels that could tap into multiple water sources or provide redundancy if one section failed. These branching networks resembled underground river systems with main channels and tributaries all carefully engineered to maintain proper flow rates. Managing the water distribution from these complex networks required mathematical skills that wouldn't look out of place in a modern engineering textbook. By the time the main tunnel neared completion, the construction crews had created something that was part mine, part aqueduct, and part underground highway. Miles of precisely graded tunnels, dozens of vertical access shafts, and a network of channels that could deliver thousands of gallons of water daily, using nothing but gravity. But all this underground engineering was worthless without the final piece of the puzzle, the surface infrastructure that would actually distribute this precious water to the people who needed it. The headworks were where engineering met politics, and trust me, that combination was about as explosive as a powder keg in a lightning storm. After months or years of underground construction, everything came down to this final surface structure where the Qanat water would emerge and be distributed to the community. Get this part wrong, and you'd have riots on your hands faster than you could say water rights. The settling basin was the first stop for water emerging from the underground tunnel. This wasn't just a simple pool. It was a carefully engineered structure designed to handle the transition from underground flow to surface distribution. The water needed time to slow down, drop any remaining sediment, and stabilize its temperature after the long journey through the tunnel system. Picture a stone-lined basin about the size of a small swimming pool, but built with the precision of a Swiss watch. The inlet where water entered from the tunnel had to be positioned just right to prevent erosion while allowing proper flow. Too much turbulence, and you'd stir up sediment that had settled during the underground journey. Too little flow, and algae would start growing in stagnant areas. The sides of the basin were lined with carefully fitted stones, sealed with the same clay and pitch mixtures used in tunnel construction. The bottom was graded with subtle slopes that guided sediment toward collection points where it could be easily removed during maintenance. Some of the more sophisticated basins even had multiple chambers, allowing sediment to settle in stages while maintaining continuous water flow. But here's where things got really interesting, and by interesting, I mean potentially deadly for anyone who messed up the water distribution. The outlet system from the settling basin had to divide the flow precisely according to agreements that had been hammered out between different families, neighborhoods, or communities. Water sharing in desert regions wasn't a casual arrangement. It was serious business, backed up by contracts, traditions, and sometimes weapons. The master builders created what amounted to an ancient flow computer using nothing but stone channels and bronze gates. Different outlet channels were sized to carry specific fractions of the total flow. A family that owned a 1/8 share of the Qanat water would have their channel sized to carry exactly 1/8 of whatever was flowing through the system. The math had to be perfect because everyone would be watching, measuring, and arguing about whether they were getting their fair share. The gate system was pure mechanical genius. Bronze or iron gates could be raised or lowered to control flow to different channels, but the really clever part was the timing mechanism. Some systems used water clocks, basically containers that would fill at a known rate, and trigger gate changes when they overflowed. Others used more complex gear systems powered by the water flow itself, automatically rotating distribution between different users according to preset schedules. One particularly ingenious system used a rotating drum with holes drilled at different positions. As the drum turned, powered by a small water wheel, different holes would line up with outlet channels, automatically switching the flow between users. It was like having a programmable sprinkler system, except it was built in 900 CE, using hand tools and bronze fittings. The social engineering was just as complex as the mechanical engineering. Water distribution schedules had to account for different needs at different times. Agricultural users needed more water during planting and growing seasons. Mills needed consistent flow during daylight hours when grain was being processed. Household users needed steady supplies for drinking and cooking. The system had to balance all these competing demands while maintaining enough flow to keep the Qanat itself healthy. Some communities developed incredibly sophisticated sharing arrangements. One person might own the water rights from dawn to mid-morning, another from mid-morning to afternoon, and a third from afternoon to sunset. Night water often went to communal pools or storage systems. The timing had to be precise, which led to the development of water clocks and sundials specifically designed for Qanat management. The mill race deserves special mention because it shows how these ancient engineers thought about energy as well as water distribution. A properly designed mill race could power grain mills, textile machinery, and other equipment while still providing water for agricultural and household use downstream. The trick was maintaining enough water pressure and flow rate to turn the mill wheels while not wasting water that was desperately needed elsewhere. Mill races required their own specialized engineering. The channel had to maintain a steeper grade than the main distribution system to generate enough flow velocity for power generation. This often meant constructing elevated channels or even small aqueducts to carry the mill race above the surrounding terrain. Some systems included ingenious flow regulators that could adjust the amount of water going to the mill based on seasonal availability. The overflow and emergency systems were where you could really see the long-term thinking of Qanat designers. They built in capacity to handle seasonal flooding that could overwhelm the main tunnel system. Overflow channels would divert excess water to storage reservoirs, or simply carry it safely away from populated areas. Some systems included floodgates that would automatically open when water levels got too high, protecting the main infrastructure from damage. But the real test of a Qanat system wasn't how it worked when everything was perfect. It was how well it handled disasters. Flash floods could fill the underground tunnels with debris. Earthquakes could crack the carefully constructed channels, and seasonal droughts could reduce flow to a trickle. The best Qanat systems were designed to handle all these challenges, while continuing to provide water to the communities that depended on them. The maintenance infrastructure was built right into the original design. Those vertical shafts that had been used for construction became permanent access points for cleaning and repair crews. The spacing was calculated not just for construction efficiency, but for the practical needs of ongoing maintenance. A crew needed to be able to reach any point in the tunnel system within a reasonable distance from a shaft, carrying tools and materials for repairs. Silt management was a constant challenge that required both engineering solutions and organized human effort. The tunnel floors included collection points where sediment would naturally accumulate, making it easier to remove during scheduled cleanings. Some systems included ingenious bypass channels that allowed maintenance crews to temporarily reroute water flow while they cleaned or repaired sections of the main tunnel. The cleaning process itself was like an underground ballet performed by workers who had to be part acrobat, part engineer. They'd lower themselves into the shafts with buckets and tools, crawl through the tunnels removing accumulated silt and debris, then haul everything back to the surface. The whole process had to be coordinated carefully to avoid disrupting water flow to communities that depended on the system. Quality control extended to the water itself. The best Qanat systems included natural filtration that removed impurities and maintained consistent water quality. This wasn't accidental. It was the result of careful attention to the types of rock and soil the water passed through during its underground journey. Some builders even modified tunnel routes to take advantage of natural filtering layers in the geology. The economic impact of a successful Qanat system was enormous. Communities that had reliable water supplies could support larger populations, more intensive agriculture, and specialized crafts that required consistent water access. The investment in Qanat construction often paid for itself within a few years through increased agricultural productivity and expanded economic activity. But the social impact was even more significant. Qanat systems created a need for cooperation and shared governance that helped bind communities together. Water sharing agreements required negotiation, compromise, and ongoing collaboration between different groups. The maintenance requirements meant that communities had to work together regularly to keep their life-sustaining infrastructure functioning. The technical knowledge required to build and maintain Qanats created a specialized class of engineers and technicians whose skills were valued throughout the Persian Empire and beyond. These master builders traveled from project to project, carrying their knowledge of surveying, tunnel construction, and water management to new communities. They were like the consulting engineers of their era, except their expertise could literally mean the difference between life and death for entire populations. Some of the most ambitious Qanat projects connected multiple water sources or served multiple communities through branching distribution networks. These regional systems required coordination between different political entities and represented some of the most complex infrastructure projects of the ancient world. The engineering challenges were matched only by the diplomatic skills needed to negotiate agreements between competing interests. The legacy of Qanat construction extended far beyond the individual systems themselves. The mathematical and engineering principles developed by Qanat builders influenced construction techniques throughout the Islamic world. The organizational methods used to manage large construction projects became models for other types of infrastructure development. Even the legal frameworks developed for water sharing influenced property law and resource management for centuries. As we approach the final phase of our Qanat story, it's worth remembering that we're not just talking about ancient history. Many of the systems built using these techniques continue to function for hundreds or even thousands of years, providing reliable water supplies through countless political changes, natural disasters, and technological revolutions. That's the true measure of engineering excellence. Not just whether something works when it's new, but whether it continues working long after its builders are gone. The numbers behind Qanat construction tell a story that would make modern project managers weep with envy. We're talking about engineering projects that achieved precision rates most contemporary construction companies can only dream of. A typical Qanat system maintained that critical 1 in 1,000 grade across distances that would challenge modern surveying equipment. Think about that for a second. Dropping exactly 1 foot for every 1,000 feet of distance, maintained over miles of underground tunnel, using nothing but weighted strings and the human eye. The crew organization was like a medieval version of a specialized construction company, except these guys were working in conditions that would violate every safety regulation ever written. The surveyor was the quarterback of the operation, responsible for the initial route planning and ongoing quality control. These weren't just guys with good eyesight. They were mathematical geniuses who could calculate complex geometric relationships in their heads while standing on a wind-swept hillside. Master diggers were the rock stars of the underground world. A good master digger could earn more than a skilled craftsman in the city, and for good reason. These guys developed an almost supernatural ability to read soil conditions, detect underground water sources, and maintain precise tunnel grades while working in spaces barely large enough to crawl through. The best ones could supposedly tell what type of rock they were about to hit just by the sound their picks made against the tunnel face. The hauler crews were the unsung heroes who made everything else possible. Picture this. You're working at the bottom of a 200-foot shaft, and every single tool, timber support, and bucket of food has to be lowered down to you by hand. Then every bucket of dirt and rock you dig has to be hauled back up that same shaft, one leather bucket at a time. The logistics alone would challenge a modern construction company with cranes and machinery. Here's something that really shows their organizational skills: the rotation system. Workers couldn't stay underground for extended periods without risking their health, so crews were constantly rotating between surface and tunnel work. The scheduling had to account for different skill levels, physical capabilities, and specialized knowledge. You couldn't just throw anyone into a master digger role, but you also couldn't afford to have your most skilled workers exhausted from overwork. The tool management system was like running a medieval hardware store underground. Each crew needed specific tools for their section of the work, but tools wore out quickly in the harsh underground conditions. Broken picks had to be hauled to the surface for repair, replacement tools had to be lowered down, and everything had to be tracked to prevent work stoppages. Some of the larger projects maintained underground tool caches at regular intervals, but that meant dedicating precious tunnel space to storage. Quality control checkpoints were built into every stage of construction. The master surveyor would regularly descend into completed sections with his measuring tools, checking grades and alignments. If a section was off by more than a few inches, the entire crew would have to go back and fix it, no matter how much work had already been completed. The margin for error was essentially zero, because water doesn't forgive engineering mistakes. The seasonal work cycles added another layer of complexity that modern project managers rarely face. Qanat construction had to be planned around weather patterns, agricultural cycles, and water table fluctuations. The best time for digging was often during the dry season when underground water levels were lower, but that was also when surface temperatures made working conditions nearly unbearable. Crews had to balance optimal construction conditions against worker safety and community labor availability. Emergency procedures were developed through hard experience and plenty of disasters. Cave-ins were a constant threat that required immediate response protocols. When a tunnel section collapsed, rescue crews had to mobilize within minutes, bringing specialized equipment and medical supplies down through the nearest shaft. Some projects maintained dedicated rescue teams whose only job was responding to underground emergencies. 1,000 years ago, Persian engineers were pulling off construction miracles that would make modern contractors break out in cold sweats. These weren't just impressive building projects, they were lifelines carved into solid rock, using nothing but human determination and mathematical brilliance that wouldn't be matched for centuries. The numbers speak for themselves. Grades maintained at exactly 1 foot per 1,000 feet across miles of tunnel, dozens of shafts per mile, all coordinated by crews working in spaces barely wide enough for a person to crawl through. When you consider that many of these Qanat systems are still flowing today, delivering cool, clean water to communities that have depended on them for generations, you start to understand what real engineering excellence looks like. These ancient builders didn't just solve a water problem, they created a legacy. Every Qanat that still flows today is proof that sometimes the old ways weren't just good enough, they were better. No electricity, no pumps, no maintenance nightmares, just gravity, precision, and the kind of craftsmanship that built things to last not just years, but centuries. The next time you turn on a faucet and water comes out, remember those Persian engineers crawling through underground tunnels with oil lamps and measuring strings. They understood something we're still trying to figure out. The best technology isn't always the newest technology. Sometimes it's the one that just works, day after day, year after year, for 1,000 years and counting.